In this video, Interdigital demonstrates the deployment of an AT3S xApp in the context of the zero-defect manufacturing use case for the 5G Dive project. AT3S stands for Access Traffic Steering, Switching, and Splitting. It is a 3GPP Release 16 feature that allows to define steering, switching, and splitting rules for the access traffic between 3GPP and non-3GPP access points. The xApp that can be deployed at the edge of networks or at Open RAN controllers is able to enhance the throughput of users, a fundamental problem in the context of the ZDM use case due to the high practical requirements of the video streaming. In this demo, the user is therefore a camera in mobility deployed at an Industry 4.0 factory. The proposed factory environment for demonstration is a 3GPP technical report compliant indoor factory scenario. 3GPP Technical Report 38.901 is a study on channel model for frequencies from 0.5 to 100 GHz. It is a report that combines the outputs of three major 3GPP studies. The goal of the report is to provide RAN1 working group, which is responsible for specifying the physical layer of radio interfaces for UEs and radio access networks with mechanisms for performance evaluation of physical layer aspects using proper channel models. The report relates to 3GPP's evaluation methodology and different models for the said physical layer evaluation. Key takeaways from this report are therefore that channel models themselves, but also indoor industrial scenarios of interest. The specific scenario of interest chosen for this demonstration follows the report's recommendations for Industry 4.0 factory facilities. A rectangular-shaped factory of 300 times 150 meters is considered. Inside, 18 5G cells are deployed. For each of the cells, the propagation of waves and other channel characteristics follow the report's recommendations. With these, it is possible to derive coverage maps inside the factory that are then used in the underlying predictions and functionalities of the app. 8 Wi-Fi access points are deployed in different areas of interest. The access points are replicas of Interdigital's own routers based on collected telemetry data that was then stored at Interdigital's data lake solution. The different Wi-Fi access points have different available average throughput, so that different combined 5G and Wi-Fi splitting rules can be observed in the demo at different factory locations. We show in the demo a camera or user equipment in mobility inside the factory. The camera's trajectory is assumed to be predicted and is displayed on screen. Based on the camera's position, the available throughput from both 5G cells and Wi-Fi hotspots is predicted for a time window of 5 seconds. The main output of the demo are the AT3S results and rules that are displayed on screen in real time. These rules have a 5-second validity timer to match the 5-second throughput predictions from the trained models at the data lake. In addition to this, and as a second output, the mobility aspects are also considered. The camera is considered to be configured with a conditional handover configuration that allows it to autonomously perform handovers based on the radio interface measurement assessment. Therefore, in this demo, enhancements to conditional handover are also displayed, where the enhancements are the prediction of the best set of cells for handover based on the predicted UE trajectory and the available information from coverage maps. In this slide, we can see an example of a coverage map distribution where the channel quality indicator is the considered metric. The yellow parts represent for each cell the antenna location, where we see the CQI degrading as we move away from the antenna system. The Wi-Fi access points are represented by red dots, and the black circles around them represent their coverage area, which is considered uniform inside each circle. The orange dot that moves around the screen is the user equipment or the camera. The camera moves around the factory following the blue line. On top of the screen in the middle, the current serving 5G cell and Wi-Fi access point IDs are displayed. On the top left corner, the conditional handover configuration for the camera is displayed in real time, showing the list of optimal handover cells based on reference signal received power. On the top right corner, there is the output of the xApp decisioning, This consists of the throughput predictions for both 5G and Wi-Fi, the result of the xApp decisioning, and the total combined achieved throughput. We can now see the demo in execution. The UE is following the blue line trajectory. As the UE moves, the list of the best available 5G cells is displayed on the top left corner. This list is being updated in real time, and it is obtained via UE-performed measurements. The list displays a maximum of 8 cells aligned with 5G measurement reporting specifications. In this demo, the UE receives a conditional handover configuration from the network, which allows it to perform autonomous mobility procedures. The UE always connects to the best 5G cell, the one that provides best radio conditions according to RSRP measurements. The UE also scans for Wi-Fi access technology as it moves around the factory. Therefore, whenever there is overlapping coverage between the two radio access technologies, the serving Wi-Fi access point ID is displayed on the top middle part of the screen, along with the current serving 5G cell ID. As the demo is in execution, the machine learning models for 5G and Wi-Fi throughput predictions perform inference for a 5-second time window. The models leverage mainly on the radio conditions data from the 5G cells and on Wi-Fi router collected telemetry that was stored at the data lake solution, and that includes Wi-Fi radio channel conditions, but also hardware utilization. Finally, the results from the demo execution show on the left the high accuracy of the trained models in blue color against 100% accurate models in orange color. They show as well the throughput gains against the 5G only baseline benchmark. The fixed splitting rules of 50% each on 5G cells and Wi-Fi access points always underperforms. A fixed rule of 75% on the 5G cells and 25% on the Wi-Fi access points can indeed overperform against the baseline 5G connection only, but it can also significantly underperform, as seen in the last column of the box plot on the right side. These results show the xApp and its derived rules enable significant gains in terms of throughput, but also, and importantly, load balancing across radio access technologies and traffic offloading capabilities to support 5G deployments.